Hey everyone, welcome back, and today let's solve Leetcode problem 2048 titled Next Greater Numerically Balanced Number. So effectively, to kind of summarize what the problem statement says, we're given an integer n and we have to return the smallest numerically balanced number that's strictly greater than n, or a number that's numerically balanced is kind of defined if every digit d that appears in that number has a frequency of exactly d in that kind of string. For example, 1333 would be balanced. Why? Because the actual digit or character 1 has an occurrence of 1, and the actual digit or character 3 has an occurrence of 3. There's 1, 1, and 3 3's in this string or kind of integer 1, 3, 3, 3, right? Hence the reason why it's balanced, right? And the kind of problem statements, or rather examples, go through the same thing. Notice how 22 is greater than 1, 1333 is greater than 1000. They're all the smallest possible numerically balanced values that are still greater than n, right? And the reason why this is balanced, of course, is again 1133's. This is balanced because 2 2's, right? And 3 is balanced because 3 3's and 1 1, and this is the smallest value that has such a property that's greater than 3000. So for the constraints here, we see that our value n is going to be between 0 and 10 to the 6th power, which is rather, at least relatively large in terms of problem statement constraints. And so we can't have too inefficient of a solution. At worst, like worst case possible, we're going to try to have probably a linear runtime complexity, because anything kind of slower than that, it would be pretty slow, and we'd probably get a TLE with our larger input sizes, like 10 to the 6th, 10 to the 5th power for like quadratic solutions and things like that. Which brings us to the main observations to really make when solving this problem, right, and how we really can solve it. And the big picture of how we're going to do this is using something called a helper method. Basically, we're using this helper method to do something to kind of simplify a check for us in this problem simulation or this problem implementation. And in this case, we want to easily check if an integer x is actually numerically balanced when we're trying to construct or form the smallest numerically balanced integer that's at least greater than n. And we don't want to keep checking if it's balanced every single time. Instead, we want to have a small helper method that does that for us so we can verify different integers that we build a lot more quickly. And so we're going to write that smaller helper function. We're going to call it, is balanced. We're going to take it a parameter x. That parameter is basically just checking whether an integer x is actually numerically balanced, right? And once we actually initialize that helper method here, we're going to then start from n plus 1, and we're going to test each integer until we actually find the first one that's balanced. And whichever one we find at first, that would be our answer, because that would be the smallest possible value that's closest to n, but still actually has that property of being numerically balanced, right? That's kind of a nutshell of how this problem works. It isn't too complex or anything, right? It's just the whole point of pre-processing or initializing or validating method here, and then just keep iterating through numbers until we actually find the first one, because that would be the smallest one that also is numerically balanced, right? And that leads us to the main observation to really make for this problem. And that is because the valid digits are actually always from 1 through 9, and the occurrences of those digits have to equal the value of that digit itself. We know that the digit 0 cannot appear, because it's impossible to have an occurrence of 0 in an actual written number. And so we don't really have to worry about 0. We simply just have to worry about the digits from 1 through 9. We can immediately reject any numbers containing 0, because that would just break the problem's kind of constraints. We wouldn't be able to use those numbers in the first place, right? Which brings us to the kind of variables and different data structures that we're going to be using. We're going to use a fixed size integer array that's going to have a length of 10. The reason why it's fixed is because we only have 10 different digits, and that is 10 different digit frequencies, and that is 0 through 9, right? Those are our actual frequencies for digits. And that's, of course, constant space because it's not linear with our input. It's simply just a fixed constant value of 10. And for our variables, of course, we're going to be working with our input. We're going to be working with a candidate, basically just the current number that we're checking until we actually find one that works. And we start from n plus 1 to make sure it's greater than n. We're also going to have a count frequency array, and we're also going to be actually taking d divided by digit, which is that extracted digit value, which we'll get into more in the actual coding part of this solution, which brings us to the coding part of this solution. And the very first thing that we're going to do, like I talked about, or rather glossed over the problem kind of solution overview, is create our helper method. And I'm going to call it exactly what I talked about. I'm going to call it is balanced. Oops. And like the name suggests, we're literally checking if this input integer parameter x is balanced, right? It's either going to be true or it's either going to be false. It's going to have a Boolean output. And basically, in this, we're basically just using this inner helper function here to validate all the numbers that we get, or all the numbers that we iterate over from n plus 1 up until the first one that's actually numerically balanced. Again, that would be our answer. Now, once we actually get that, we're then gonna actually create an integer list. I'm gonna call it count, and it's gonna have 10 zeros. It's gonna again have a fixed length of 10. It's basically just gonna hold the counts or the frequencies from the digits 0 through 9. And of course, this is constant space memory because it is a fixed length of 10, right? It's not linear or based on or reliant on our input size n, right? So I'm gonna call it count. And it's going to be all zeros for now with a length of 10, so we can just multiply it by 10. Once we do that, now we're actually going to start a loop to actually, or rather, we're going to start a variable or create a variable to actually kind of set it equal or iterate over x while actually extracting our digits. And we're simply going to copy x into y, so we don't actually kind of mutate the callers x while we're actually working with and extracting it here, right? It's not strictly necessary in terms of this solution, but it is pretty clear to work with and intuitive when I do it like this, right? So I'm going to set y equal to my integer x. Again, note that x is simply just my parameter or input, if you will, that we're passing in to this isBalanced method here, and we're just currently setting y to be equal to x. We're simply using this variable y to iterate over x while actually extracting our digits and keeping track of their frequency. And the whole reason why, again, we're copying x into y is that we don't actually mutate the callers x, right? That's the whole point of this kind of copying over part, if you will. Once we do that, now we can actually begin our loop here. And it's going to be a while loop here while y is greater than 0. Essentially, this is like our first kind of pre-processing validating loop. We're basically just using this loop to extract our digits here. So while y is equal to, while y is greater than 0, we're going to take the last digit d equals y modded by 10, right? D is simply just representing a digit value, and we're going to increment its count because we'd see it one more time. We'd have a frequency of one more, and then we have to actually integer divide y by 10 to drop or kind of remove that last digit kind of mathematically, right? So while y is greater than 0, we're going to extract our last digit to be y modded by 10. Right, we're effectively just inside this loop extracting that and storing it in this value d. And then from here, we know if d is 0, notice how we talked about in the solution explanation, we automatically reject it. We automatically reject such numbers that have zeros in them because any number with a 0 has to be false. Any number with a 0 cannot be balanced because we can't have 0 of something. The moment we see a 0, we know it has a frequency of at least 1, which it can't because 0 should supposed to have a frequency of 0, which means our any balanced numbers cannot have zeros. And so if we see a 0 in this input, we immediately return false. Any values with zeros cannot actually be balanced, right? And so that's kind of the main observation that we also talked about in the problem overview. Right now, what if d isn't 0? Well, then we can keep going. Then we can increment the d's value or the d's kind of frequency and then reject it or remove it from our current y or our current x. And so we're going to count at d and increment its frequency by 1. We're simply just incrementing the count, if you will, of this specific extracted digit d. Once we do that, we're going to then drop this last digit d from y. We're simply just going to move to the next digit. And the way we do that kind of mathematically is simply using integer division, more specifically by 10, because it is the units place, or it is kind of that position place in an integer. And so we're going to divide by 10, and that was a completely weird way to do it. Sorry, I don't need that extra equal sign. We're simply just dividing y by 10, right? Effectively, we're just dropping it from y by moving on to the next digit. Now, once we actually process once we actually process all the digits, once we exit this while loop here, when y is no longer greater than 0, now we have to actually verify if this is balanced. We have to actually verify if the counts actually match the digit values now that we've actually incremented the counts, right? And so we're basically just going to loop digits from 1 through 9 because, of course, 0 is kind of already banned, if you will, or forbidden. And if a digit has a non-zero count, we know that that count has to actually be equal to that digit's value, right? That's the whole definition, like the problem statement says, of if an integer is numerically balanced, right? There are exactly d occurrences of an integer or digit d in an integer or in a number. And so how are we going to check that? Well, again, like I just talked about, we're going to iterate over all the digits from 1 through 10, or specifically 1 through 9. In Python, it's 1 through 10 because we're going to go up until 10 exclusive or 10 minus 1 inclusive, which is simply just 9. And for every digit in this range, in fact, I'll call it digit just so it makes a little bit more sense, and instead of just using my I as my iterator, if the count of my digit is greater than 0, meaning it's non-zero, and the count of the digit is not equal to the digit itself, we can't do it. We can't actually verify this or validate this. We have to immediately return false. Again, why? This breaks the definition of a numerically balanced integer. If the count at digit is not equal to the digit value itself, the integer isn't numerically balanced, because that's the whole definition of an integer being numerically balanced. And so if this condition isn't true, even if its integer frequency is greater than 0, we immediately return false. Now, what if this check actually does pass? What if we do actually have a frequency of the digit that actually matches the digit value? Well, great. It actually does kind of pass in or align with our defining property, and so we can just continue on to the next loop. But if we ever return false, if this condition ever does not hold true, that's when we return false. And finally, we'd return true at the end of this for loop here if we didn't return false for any of the digits, meaning all checks passed. That means this integer x is fully balanced, and only then, once we exit this loop for all the digits, that once we actually verified all the digits potentially, then only can we return true. That means it is actually a balanced integer. Now, that's the whole kind of setup for our helper method here. Now that we're done with that, the rest of the solution is actually very straightforward. It's literally just iterating through all the integers after n plus 1, or rather after n, I should say, and finding the first one that's numerically balanced, because that would be the smallest one as well. That would also be greater than n. And so quite literally, we're simply just going to directly implement that. And the way we do that is essentially just starting off with our candidate, right? That's going to be our possible answer, and it's going to start off at n plus 1, because n plus 1 is the smallest integer that is greater than n, and this is our first candidate, or possible candidate, that could be possibly numerically balanced, and we keep incrementing it by 1 until we actually get our smallest possible value that's still greater than n, but is also numerically balanced, right? That's basically just our starting value that we're going to check first, this candidate value. Now, while true, this is just basically our validating loop, right? We're simply just looping indefinitely until we actually find a balanced numerical integer, right? So basically, we're just checking each candidate with the isBalanced helper method here until we actually find one that returns true, right? And when we find it, we actually return it as our answer, because it's the smallest numerically balanced integer that's greater than n. And again, leading back to that main observation, balanced numbers are pretty sparse, but because this our inputs are actually limited, this loop would terminate quickly in terms of like the Leetcode parameters and the Leetcode input test cases, and so that really isn't something that we have to worry about. Now, for every value or candidate until we actually find one, so while true, if is balanced at this candidate integer is actually true. Now, one way to do this in Python is set it equal to true, meaning it is numerically balanced. Or you can just do this. That also checks if it's true. If it is true, we return candidate, right? Because that would mean that great, candidate is actually numerically balanced, and I think that's how you spell it. Yeah. Now, what if this doesn't return true? What if we don't actually fall into this conditional? Well, if it doesn't return true, if we don't return candidate, well, then we have to actually otherwise increment candidate by 1 and then continue searching on until we find one. And so we then increment candidate by 1. Oops. And we keep doing this while true until we actually find a candidate that is balanced, that does actually return true and verify or pass this isBalanced helper method test. And that is it for our solution here. And if I submit this, this would actually be accepted, and this would be a valid solution. And as you guys can see, once this actually submits, give it a minute. Oh, sorry, I forgot to increment this by 1. Let me resubmit. Sorry about that. Small error there. But now, as you can see, once we submit, this is actually accepted, and this is actually a valid solution. So as a whole, how are we really solving this problem? Effectively, we're just creating our isBalanced method to count the digits in a candidate number, and we're verifying every non-zero digit d appears exactly d times. Once we do that, we're simply just trying every number that's bigger than the input value that we start off from candidate, which is n plus 1, until we actually find the first one that passes the isValid check, and it's very, very straightforward, right? And again, another main observation here, because the digit counts must equal the digit values, there's only a few possible patterns, right? For example, you can never have a number with 2 different digits both equal to 9, because that would require both 9 plus 9 equals 18 digits in total, which would explode our input length. And so because of this sparsity, that's why scanning from n plus 1 works pretty quick for these Leetcode inputs. Which brings us to the runtime complexity here. Really kind of as a whole, it would be big O of c times the log of c, where c is basically the magnitude of our candidate. And the reason why is because for each candidate we do a digit scan that would cost big O of d, where d is simply the number of digits, which would equate to log 10 of candidate. And if m is the gap from n to the next balanced number, the worst case time for that would be big O of m times d. Now, in these kind of typical inputs in Leetcode that's bounded by 10 to the 6th, m is pretty small and d is also guaranteed to be less than 7, and so this is pretty fast, right? And for our memory or space complexity, it's actually going to be constant, believe it or not, or big O of 1, because we are actually using only a fixed length array called count. It's always going to have a length of 10, and so this is a big O of 1 memory complexity. We're only using a few extra other integer variables, but that's not going to change regardless of our input size, right? It's always going to be constant space, right? So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.